Welcome to topic 4.7, types of chemical reactions. The learning objective for today is 4.7.a, identify a reaction as acid-base, oxidation reduction, or precipitation. So there are several types of reactions that you should be able to distinguish at this point. We're going to go into much more detail about each of them as we move through the course. So the focus at this point is just to identify the type of given reaction. And of course, that also includes balancing it. So we're going to start with precipitation. So a precipitation reaction is the formation of an insoluble ionic compound from two aqueous solutions. So if you have AB plus CD, that would yield some solid, which could be AD, and then the aqueous ions that caused those components to dissolve in the first place would still be present, but they would still be in aqueous form. We've already talked about precipitation reactions because we usually use them to introduce the concept of net ionic equations. So an example of this would be the combination of lead nitrate and potassium iodide to form the precipitate lead iodide. Next, we have acid-base reactions. We already talked about that, which is also known as neutralization. In acid-base reactions, you have the transfer of an H plus ion from an acid to a base. So that would look like this. So you have an acid because at this point, we're going to assume that all acids start with the element H, hydrogen, which is actually going to be a good rule of thumb for acids moving throughout the course. And then we've only talked about strong bases at this point as well. And so strong bases are column 1 and 2 hydroxide. So X here would be something from column 1 or 2. So then when these two combine, that hydrogen and that hydroxide, which are freely moving about in solution, find each other, they come together to produce liquid water. And then, of course, your cation and anion that remain from your base are still dissolved in the solution in aqueous form. So, for example, you can have hydrogen. This says hydrogen chloride. It's hydrochloric acid and sodium hydroxide, and they would mix to form sodium chloride and water. So then finally, we have oxidation reduction reactions, also known as redox. So redox is the transfer of electrons from one species to another, and that might look like this. When you lose electrons, that's called oxidation. When you gain electrons, that's called reduction. I'm going to talk about that much more in just a minute. So if you want to look at an example, whoops, that one didn't zoom for me. An example of this might be solid zinc reacting with a copper in solution to form zinc ions, which would move into the solution, and then copper solid, which would be plated onto the original solid surface. This terminology here, reducing agent, oxidizing agent, you will see, but it is no longer required of you in AP chemistry to use that terminology. So you might have heard of some other specific reaction types in previous classes or elsewhere online, and actually all the other specific reaction types that we talk about are applications of redox. So I just want to run through them because you might see them in this class, and I want to talk about what some kind of boundaries are for AP chemistry. In AP chemistry, the only addition reactions you need to be able to predict are the formation of binary compounds from their elements. By the way, you might also heard addition called combination or synthesis. So when we're looking at these addition reactions, you want to make sure to watch out for diatomic elements. Remember the 7 diatomic elements, and always remember to balance both the number of atoms and charge. So a classic example of this is the reaction of aluminum with oxygen in the air to form aluminum oxide, which you can see here as kind of the brown marks that are on the surface of the solid. So we have a lot of oxidation reactions that occur in air that cause metal to form oxides. And so this should have a state of solid there. Notice that we have paid attention to balancing here, as well as paid attention to the fact that oxygen would be a diatomic. The opposite of addition is called decomposition. So an addition reaction has 2 reactants that combine to give one product. A decomposition reaction has 1 reactant that breaks down to give 2 or more products. Predicting the products of decomposition can be challenging. Now, we actually saw this in the lab. We did the decomposition of baking soda, and we saw that there are 4 possible ways that might decompose. Of course, it only did 1, and that's what we were testing for. Now, in AP chemistry, the only type of decomposition that you need to know is that all binary compounds break down into their elements. And again, you want to give consideration, just like in addition, to the number of atoms and the charge. So an example of this that's really pretty cool is the electrolysis of water. And so when you have the electrolysis of water, it's all you do is you put electrical current through water and it will decompose into hydrogen and oxygen. And so you can see that here, bubbles being formed at the surface of the electrodes. And then, of course, you can see the bubbles rising in these two tubes. This particular apparatus is really cool because it allows you to see the mole ratio that exists in the water. So you can tell that this front tube here, that is the hydrogen gas that's being collected. And over here we have the oxygen because this has got twice as much gas in the tube as that one does. So that's pretty cool. So then we have specific redox reactions continued. We have single replacement and combustion. And those are both, again, applications of redox. We're going to explore single replacement much more in Unit 9, but I do want to talk about combustion for a second. So the products of the complete combustion of a hydrocarbon is just a compound that's made of carbon and then a number of hydrogens that's necessary to complete carbon's octet, just depending on the bonds that exist between the carbons. So if you have the complete combustion of a hydrocarbon, that would always give you carbon dioxide and water. And this would also apply to the complete combustion of compounds that contain only carbon, hydrogen, oxygen. Now, if you add in if there is another type of atom that is present in the fuel source, then obviously you will have some different products because those atoms have to go somewhere. Additionally, we can have incomplete combustion, which might form other byproducts, for example, carbon monoxide. Okay, so redox reactions, to get into some specifics about them. So in redox reactions of all kinds, you always have two processes happening at the same time, oxidation and reduction. So a substance being oxidized is one that loses electrons, and a substance being reduced is one that gains electrons. And so you can remember this with Leo the lion. So Leo the lion says GR. Leo stands for lose electrons equals oxidation. GR stands for gains electrons equals reduction. So if you like Leo, you can remember that one. I also quite like oil rig. So oil rig stands for oxidation is loss, reduction is gain. So remember, if you have oxidation, you must also have reduction and vice versa, because those electrons have to go somewhere. They're not just floating around willy-nilly. If they're lost on one side, they're gained on the other. So then how do we figure out what's being oxidized and what's being reduced? Well, we use something called oxidation numbers. So we assign oxidation numbers in the following order. So this is a hierarchy and you must do them in this order. First of all elements are assigned an oxidation number of 0, period, done. Elements in their elemental form. You are again going to watch for diatomics. We follow that up with monatomic ions, so ions that are just a single atom. Those oxidation numbers are going to be the same as the charge. Now, from here, oxidation numbers and charge can differ. For 1A and 2A metals, they're going to be +1 and +2, which is the same as the charge. Same for fluorine. Now, again, remember, if you have any of these in their elemental form, that's not true, then their oxidation number is going to be 0. Oxygen is usually -2. A notable exception to that is when it is peroxide, in which case oxygen would be -1. So, for example, H2O2. From there, things get a little less aligned with the charges. Hydrogen is usually +1. That's always true if it's paired with a nonmetal. And then your common ions are the typical charges. Again, not always true. So sometimes we see things like nitrogen, which we normally expect to be -3, can actually sometimes have an oxidation number of +5. Okay, so you do need to assign oxidation numbers in this order, and you more or less need to know this order. So remember, we go elements, then we go monatomic ions, 1A, 2A, fluorine, oxygen, hydrogen. For the most part, if you assign the common charges and then you go and work backwards for anything else that you can't identify by using common ions, you'll be able to figure it out most of the time. So then, oxidation numbers for atoms in a compound, including polyatomic ions, always add up to give the overall charge of that compound. So that's how you can figure out an oxidation number that might not be immediately obvious upon initial inspection, because you can figure out what it would need to be to make the overall charge equal to whatever you've been told it is. In compounds, negative oxidation numbers are assigned to the more electronegative atom, and oxidation numbers of the same charge are not found on neighboring atoms. So again, all these are little pieces of the puzzle to help you figure them out. So here's a simple example for you, is rusting a redox reaction. So here we have iron, and oxygen in the presence of water forms Fe2O3. So let's assign oxidation numbers. So iron is in its elemental form, so it's going to be 0. Oxygen is in its elemental form, so it's going to be 0. On this side, we're going to be able to, we don't know the iron oxidation number off the top of our head, but we do know oxygen is going to be -2. So those went out of order for me. If we know that oxygen is -2, then we can multiply that by 3, and that will give us an overall -6, which then, to make this neutral, has to be shared among the two irons as +3. So this is going to look a lot like the same process you guys did to determine the ionic compound that is formed from ions. Okay, but you can tell here now we can use the same process, because we go from 0 to +3. So oxidation is loss of electrons, meaning it's becoming more positive. This one is oxidation. Reduction is gain of electrons. Electrons are negative, so that would make it more negative. So here is the reduction. So then here's a question for you. Is the reaction shown below redox? Justify your answer by assigning oxidation numbers. So if you want to go ahead and try this on your own, you want to pause the video now, because I'm about to go through the answer. Okay, so we're going to start with elements in their elemental form, which is going to be oxygen. Here is going to be 0. Then we would look for monatomic ions, which we do not have in this sample. All right, so then where do we go from here? Well, we're going to look at fluorine being a -1, because we don't have any column 1 or column 2 species here. Remember, hydrogen is its own thing with its own rule further down. So we're going to assign that fluorine is -1, that fluorine is -1, that fluorine is -1. Now we're going to come back and we're going to make oxygen, or we're going to make the hydrogens +1, and we're going to make selenium, then we know can be -2. And then because this fluorine was -1, oh, I'm not there yet, sorry. Because this fluorine is -1, we know this selenium is going to be +6. There it is. Because this fluorine is -1, that fluorine must be +1, right? Which is a little bit unusual, because fluorine is more electronegative than oxygen. So fluorine then has the negative oxidation number, meaning oxygen is left behind with a positive oxidation number. Again, unusual for us to see that in oxygen. So is it redox? Hydrogens all stay +1. Selenium starts as -2 and goes to +6. There is a change in oxidation number for selenium. So selenium is experiencing a change. And then we also have a change in oxygen from +1 to 0. So then selenium is becoming more positive, which means it is losing electrons. And then oxygen is becoming more negative, so it is gaining electrons. So selenium is being oxidized and oxygen is being reduced. So yes, this is a redox reaction. We're going to do a CER. Evidence: if you are asked to justify if it is a redox reaction, your evidence will always be oxidation numbers. So the oxidation number for selenium changes from -2 to +6. The oxidation number of oxygen changes from +1 to 0. And so our reasoning is, because the oxidation numbers of selenium and oxygen change, this must be redox. If you're asked to identify specifically which side is undergoing oxidation, which side is undergoing redox, you can do that as well. That would make it an extra strong answer. So then I just wanted to show you real quick that there are a lot of possible oxidation states. So up until this point, you've probably mostly thought about charges, and you haven't even thought much about oxidation numbers. So where we are used to maybe seeing some variation in charges with the transition metals, I also want you to know that oxidation states can be even more varied than that. So if you look here, anywhere where you see the kind of darker shades, those are all the possible oxidation numbers. Some of them are more common in nature than others, and those are the ones with little circles around them. Okay, so what should I be able to do with this? You should be able to classify a reaction by identifying the transfer of species: a transfer of protons, which is acid-base, a transfer of electrons, which is redox, or a transfer of ions, which would be precipitation. You should be able to determine if a species is being oxidized, reduced, or neither by assigning oxidation numbers. You should be able to complete a combustion reaction of a hydrocarbon, and you should be able to use these SNAP ions to identify the product of a precipitation reaction. And that is it, and I'll see you guys in class.